Thank you, Aaron. I'll just start by saying it's being recorded. So, okay, thank you very much for showing up this Friday afternoon. I'm on the West Coast, so it's a lunchtime for me, so it's not too bad. And sorry for the East Coasters that are almost their Friday afternoon. Thank you. So we're all gonna talk about today is about DMR++. This is Chunk Manifest, essentially developed, maintained by OPeNDAP and within the NASA ecosystem, and we're really excited. There's all of this interoperability uh, that's happening right now in the ecosystem. Aaron put in the chat there a Google document. I'm going to check it out, but yeah, perfect. So we'll do when you have a time, do a roll call. And I'm gonna maybe let's wait 1 more minute before getting started. James gets settled. So we're gonna have James Gallagher, the president of OPeNDAP, to give us a talk about all about DMR++ today, and then for this session. And I think if you're ready, James, you can take it away.
Hmm. Okay. You can hear me?
Yes, yeah.
Okay, great. So I think I'm going to give myself about 40 minutes for these slides. I know that's a lot, but since it's a fair amount, you should feel free, of course, to interrupt me as I go along if there's something I say that seems off or you don't understand. So what we're going to talk about is DMR++. Um, the subtitle is, towards a standard chunk manifest for cloud optimized scientific data storage. The overall goal here of this particular set of presentations between now and July is to develop a chunk manifest standard or a draft standard that will focus on the content of the chunk manifests. Not so much how they represent that content, although for today's talk and probably all the others, I can't really get away from the particular way the information is represented, because there is some sort of contextual semantics that we need to talk about. But anyways, let's talk about motivation and context. So what's the motivation for chunk manifests? Why do we even care about this? So we have large, complicated scientific data sets that are chunked, and they are now being stored in these web object stores. So the challenges are we have these hierarchical data structures. They're heterogeneous in term the data themselves are heterogeneous. And we have these old data formats like HDF4, HDF4 HDF5, and so on. They really require an API to be read efficiently. And that means that API needs to have random access. It needs to be working on a random access file system or a POSIX file system. So the problem we have is that we want to be able to move these to a data storage system that is not a random access file system. And we still want to be able to access them in a relatively performant way. And so for me and for the people in OpenDAP, sort of the aha moments were that Amazon's S3, which is the web object store that NASA is using and NOAA as well, and a bunch of others, that it supports range gets, HTTP range gets. So you can do more than just get the whole object. You can ask for parts of it, and you can ask for parts of it by saying, I want you to get me data starting at this byte and go for so many more bytes. So you can get little pieces of it. I'm just calling them pieces because if I use words like blocks or chunks, that's going to get confusing fast. And then we knew also that HDF formats, they can be read this way. And we knew this because of this HDF4 mapping project that Ruth Doerr and Kent Yang worked on. But why do this sidecar manifest thing? Why put this chunk data in a sidecar file? And so there are a couple of reasons that OpenDAP chose to represent the chunk manifest in the way we did. First, we had already developed two versions of the data access protocol, and they were pretty heavily web-based protocols. And DAP4, which is the newest version of it, used this representation called DMR. And the DMR is a metadata response that does one thing that's worth mentioning, and that's that it combines the kind of metadata that scientists talk about when they use the word metadata with the kind of metadata that computer scientists are talking about when they use the word metadata. So we call the former semantic metadata and the latter syntactic metadata. And the thing that we realized is that this chunk information, the information that tells us where the bytes for a particular variable are stored in a file and how they're encoded, that's a kind of syntactic metadata. And so we could slip that into the DMR, and in a way that would associate particular pieces of syntactic metadata, this chunk information, the storage information, with the variables that they're correlated with. So that's part of it. That's part of the reason that we chose to augment an existing representation. We knew that S3 is expensive, the access is expensive, so we knew that we had to minimize data movement. So we chose to put all of the metadata in one thing so that it could be accessed in one shot. We knew that the latency is high for S3, but the transfer rates, once a transfer gets going, are pretty fast. We decided that the chunk manifest should be, that the way it describes a data set should be relatively portable. That even though our initial task was just to support HDF5, we would probably want to support other formats. And we've had some success on the interoperability scope with both Earth Access and Virtually Czar. So what is a DMR++? Well, I've already pretty much covered this, and I need to sort of pick it up a little bit, I think. So we've augmented the DMR by adding this additional syntactic metadata. And over here, I can't, over in the lower left corner, we see a sort of a schematic representation of a DMR. And at the very top, it's got some metadata that describes the rest of the granule. It's got some other information. And then we start in with the chunk manifest itself. And we see a blow up of what that kind of information looks like for a particular variable. There's an XML element called chunks. It gives you some attributes that tell you some things. There's another element called chunk dimension sizes. We'll get on this. We'll talk about this in much more detail in a bit. Then there's some other data there. The scope of the data that can be described is the same as the scope that the DAP4 protocol can describe. So there's in the lower right corner, we see atomic types, unsigned N64s and so on, containers, which include groups and arrays and structures, and then the responses, the metadata response, the DMR, and the data response. How does the DMR work? Well, it's a static file, and we build the DMR++, we build the DMR++ by analyzing static data files, not ones that are online per se. And then we load this object, it's an XML file, into the S3 store. We put it right next to the granule it describes, and we differentiate the two by tacking on the extension .dmrpp. Pretty straightforward, really. At the winter ESIP meeting, we ran a comparison workshop where we talked about the differences between Czar, DMR++, Kerchunk, and DMR++, and a few other things. And these are the kind of Venn diagrams that we came out of. I'm not going to try to speak to all of this because there's quite a bit of information here, but everybody realizes that there's a fair bit of overlap between these three technologies. And there are more Venn diagrams associated with this, and you can go back to the information from that workshop and learn about that stuff. But we did do a little tabular analysis here, and we came up with these things. And we see that there's a lot of overlap, right? They're all using byte offsets. They all encode chunk position in an array. They're all representing their information in a human readable fashion. Ice chunk isn't on here. I don't think that's true for ice chunk. Two of them, DMR++ and Kerchunk, also allow inline data references, We'll get to that later. We don't know much about heterogeneous chunk level encoding. Probably talk about that in a bit. A few other things we see that are pretty much common, but there are a few things that we still have to resolve. And that's kind of what these presentations are about, trying to resolve some of those question marks there. So now I'm going to go through a technical description of the DMR++. And then I'm going to use a lot of XML language when I do this, and I apologize for the people that have an allergy to XML. I did too, but I somehow have overcome it, at least a little bit. Anyways, I'm going to talk about what we had to do in an absolute sense, and say up front that we're probably not done. Trying to replicate the features of HDF4 or HDF5 is a monumental task. So I'm sure that there are some HDF4, HDF5 files we can't read. And then also what we had to do in a practical sense, because there are some places where we had to optimize access, and we made some choices there that might seem a little surprising, but they work out well for us and the NASA data that we were working with. So again, we're back to the content of a DMR++, and this is a slightly bigger picture, so you can see a little bit more, but you see that after the initial XML element that says dataset, which now has some new things. They're in the DMR PP namespace, and the key one is the href attribute that shows up there. And then in the next section, there's a kind of a metadata block, and that has dimensions. Those are shared dimensions. They describe the dimensionality of probably multiple variables in the data set. And then we see float 32, name, time. So that's the introduction of a variable. Then just below that, and for some reason I don't have a pointer that I can do much with, we have, you can see the actual chunk manifest. It starts off with the element DMR/PP chunks, and then we see chunk dimension sizes, and then we see the chunk information. And this repeats for every variable in the data set. So I'm now going to talk about the basic elements in the chunk manifest. And so the core XML elements hold three different types of information. The first one is DMR/PP chunks, and this holds a series of optional attributes that describe the characteristics of all of the chunks that hold the data for a particular variable. So the chunks element is one that contains child elements in it. And the chunks element contains two child elements in most instances. It contains a chunk dimension size element that tells us the logical size of the chunk. So this enables us to say that this particular chunk fits in this space in an array. So suppose we had a 100 by 100 array, we might have the chunk dimension sizes be 50, 50, 50 by 50. So there'd be four chunks in that array. One in the upper left corner to 0 to 50, the next one in the upper right corner, 50 to, I guess, 99, and so on. And then we have below that one or more chunk elements. Each chunk element has three required attributes. The offset, that's the byte offset of where the information begins in the file or object. N bytes, that's the number of bytes. So those two things tell you the size of the chunk, how many bytes you need to pull out of the object to get the chunk. And then the chunk position in the array. Again, that gives you the logical position of the chunk in the array. Chunk dimension sizes is just a list of integers separated by spaces. So it's very easy to parse. Like you can use things in just about any programming language to parse it. As I said, offset, n bytes, and chunk position in an array. These are all required attributes. All of the attributes of chunks, the enclosing element, they're all actually optional. But in most cases, you'll see the same sort of stuff. You'll see compression type, you'll see deflate level, and you'll see byte order. So here's another picture that reiterates my 100 by 100 size array with the chunk sizes, chunk dimension sizes of 50 by 50. And you can see how it all fits together. And I've noted the two places with little red rectangles there. Um, so unfortunately, even now, things can start to get complicated. In the upper example, we see where the little arrows are going. We see the word deflate appear twice. And we see deflate level appear twice. And that's because the order in which the filters are listed in the compression type attribute is the order that they're applied. And when you see deflate twice, that means that for the chunks that this particular chunks element describes, the deflate filter was applied twice, not just once. And it was applied the first time with a deflate level of 4, and the second time with a deflate level of 1. In order to inflate the chunk, you have to run inflate twice. You don't actually have to feed it the deflate level, but you still have to run it twice. We include deflate level for a reason I'll describe in a bit. In the second example, you see that 3 filters were used, Fletcher 32, shuffle, and deflate. And so when you're decoding these chunks, so that's the order in which they were used when the chunk was written. So when you decode these chunks, you have to reverse that order. You apply deflate first, then you apply the unshuffle, or actually you apply inflate first, then unshuffle, and then you compute the Fletcher 32 and see if it works. Okay, so the order matters, and sometimes the same filter is applied more than once. Both things were initially surprising to me, but there you go. There's another thing that we've so far not touched on, and that's the nature of fill values in these data. Remember we said before, let's go back a couple. Let's go back to this one here. See how we've got a 100 by 100 and chunk dimension sizes of 50 by 50? So that implies 4 chunks, right? And then we see down below, there are 4 chunks there, just as you would expect. What if there was only 3 chunks there? What would happen then? What if one of those chunks was missing? Well, it's not an error in the reader or the writer or the DMR++. Some chunks are just missing. And what that means is that those chunks consist only of the fill value. The fill value you can see in the upper right attribute of the chunks element is minus 9999.000. So in that case, the interpreter needs to synthesize those values, needs to realize that it's not going to get those values by reading the file, but instead needs to allocate the proper amount of memory space and fill it with the fill value. Fill value is one kind of sort of missing data. The chunk simply doesn't exist, and so the DMR++ interpreter has to recognize this fact and must insert the data into into whatever memory it's writing the results. Here's another example, DMR++, that shows another type of missing data. So one of the things that we have done in the past with NASA data is we've taken data files that were originally designed to be read with the HDF EOS APIs, and those APIs synthesize the georeferencing data associated with the measured parameters. But users and the CF conventions expect those data to be held in the data sets as variables. So our server in the past, when it's been working with the files and these APIs, has made those things appear as if they're variables in the data set. When we transitioned to DMR++, in order to maintain that presentation, we decided to put these values either in the data set, in a way I'll touch on in a moment, or in an additional sidecar file. And we're illustrating that additional sidecar file here. And also, we're sort of, getting to another point, which is while it's possible to have one href for the entire data set, it's also possible to assign different hrefs for each chunk in the DMR++. That's actually kind of important when you come to thinking about virtualization, because you'd like a single variable to come from many places, potentially. But anyways, in this case, we're saying that this particular variable's value doesn't come from the original data set. It comes from this file that holds the missing variable information. Okay, so that is kind of the basics of DMR++. And those things were arrived at because NASA presented us with a variety of requirements and said, can you please make all these things work? But they also presented us, in effect, with a series of other requirements. And so these are the things that we had to do to address serving collections that we were asked to serve that kind of fall out of, say, the normal logic of a chunk manifest. Some of these things are not well suited to chunked I/O, and there are others that are simply optimizations. So for non-chunked array data, HDF5 can store this as what I believe it calls compact. And what we do in that case is, instead of saying, oh, well, here's the chunk where it is, because there really is no chunk, we simply read the values in, we base 64 encode them, and we put the base 64 encoded values into the XML document, into the DMR++. Similarly, in some cases where the variables are not part of the data set, the case that I just talked about a moment ago, where the georeferencing information of the HDF EOS APIs, the HDF EOS APIs generate the georeferencing data and make it appear to be a variable in the data set, and we then replicated that feature. We don't necessarily put those values in a sidecar file. If the values are small enough, we can put them in the granule itself. Well, I'm sorry, in the DMR++ itself. And we do that again as base 64 data that are compressed. Another thing that does not oftentimes fit the chunked I/O model are string array data. So these are like 1- and 2-dimensional arrays of strings. HDF5 has at least 2 types of strings. We support varying length string arrays and fixed length string arrays. Varying length string arrays are not easy to work with in using a chunked I/O scheme. And so what we do is we read all the values into memory, and then we write them to the DMR++ using a kind of run length encoding notation. Fixed length string arrays, they may actually work well using chunk data, but we may look at those and say, well, it's better to bring them in and store them using the same base 64 encoding that we use for the compact data. Excuse me. And so this is the part of the presentation where I'm sort of talking about the outliers. So I'm going to talk about a few other things. And these aren't necessarily things that sort of break the chunking model, but these are, again, outliers. So the DMR PP chunks element, remember, of the 3 elements, that's the one that sort of encases all the information about a particular variable and the chunks that it holds. We can have an attribute there that's called LB chunk. And LB chunk provides a hint to the DMR++ interpreter that says, in this chunk, you may find this type of storage called a linked block. So you need to look for that. And if the LB chunk attribute of a chunks element, if that attribute is false or not present, false is its default value, then the interpreter knows it doesn't even need to think about these linked blocks. But if it is present and its value is true, then the interpreter needs to check and make sure that the chunks aren't actually using this linked block, I'll say technique. In addition, there's some other attributes for the DMR-PP chunk element itself. So remember, chunks is the encasing XML element. It holds a bunch of individual chunk elements and those chunk elements hold the actual offset and length for the data blocks. So data pieces, better word to use in that case. Okay, but anyways, we have these two extra attributes. One is called trust, and trust simply says, hey, if this chunk has its own href, you don't need to validate it. You don't need to ask if it's okay to go get these data. It's already been done. And this is just a trick we use to help smooth operate flow of data through our system, because validating URLs when there's thousands and thousands of them gets computationally expensive and wastes time because we already know the answer in a lot of cases. There's another thing called FM. It's a bit of a mysterious name, but it stands for filter mask. And what we're recording there is whether or not the metadata in the HDF5 file indicates that one or more of the filters for a particular chunk did not succeed. And so this is a piece of metadata information that we will want to use in some optimizations that we have coded. But you don't technically need to know this to read the chunk off disk, but you probably need to know this if you want to decode it if any of the bit flags are set. If the value of FM is 0, then you're being told that all of the filters worked just right. And so you can expect inflate, unshuffle, and Fletcher 32 to work, like in the previous example we had back at the beginning. So those are sort of outlier attributes. They're a little bit obscure. There's also some parts of the DMR++ that are just for HDF4. We have an element called the block, DMR-PP block, and that's because some HDF5 files, you don't use chunks to store data in an array. They use something else called a block. And the algorithm for working with blocks is slightly different than the algorithm for working with chunks. More explanation if needed. And then we have DMR-PP chunk can have an attribute called the linked block index, and that sort of correlates to the thing that I mentioned in the upper left corner there, LB chunk, the Boolean. This is the attribute that the interpreter would be scanning for if LB chunk were true. And if the linked block index tells you how to combine multiple chunks so that they can be treated as a whole. In HDF4, a chunk is not an atomic unit of storage the way it is in HDF5 or the way a chunk is in ZAR, where you never would break up a chunk in ZAR, right? It's atomic in the old school view of the word atomic. So anyways, here's some examples of these things. Here's a DMR-PP missing data element. This is for the lawn dim. And in this case, instead of referencing a sidecar file, the values are right here. And that's probably because this is level 3 data, and level 3 data, the missing data, is usually a vector. And we can see that, in fact, lawn dim and lat dim, they're vectors. They have one dimension. Here's another example of compact data. And this time, this is, I don't know what this is. I kind of recognize this granule. But anyways, this is just an integer, an int 32 variable. It's the granule pass fail. And you can see it's got a chunks element, but the chunks element doesn't actually contain anything. And it's got this compact notation. These are the values for that 32-bit variable. And this also shows a kind of a problem with base 64 encoding, right? I mean, it actually takes more bytes than the 32-bit array or 32-bit integer would take, but yeah, doesn't really matter. Um, it's less, so here's some more or less common stuff. So here's what a DMR PP block looks like. So this is an HDF4 file, and it's a two-dimensional variable. And what's happening, you notice, for example, that the inside the sort of pink rectangle, byte order is BE, is big endian. So I believe all HDF4 data is stored in big endian byte order. So that means that an interpreter has to be savvy. It has to understand that in order for these values to actually mean something, the byte order has to be switched around. Not super hard to do, but it's an extra step. Um, Here, the three blocks are joined together, and then decompression is applied to the result of that. And that's kind of that's a thing. Um, and so that's what the block element is about. And then here's the linked block example. So we see LB chunk is true in the chunks element, and then down here in some of the chunk elements, we see that linked block index is 0 and then 1. And what this shows is that the first chunk, which has 365 bytes, is the one with the block index of 0, and it gets joined to the one that's got the block index of 1. And there's only 2 bytes there. And I wish that I could get my mouse pointer to work. And I know there's probably a fancy way to do that. But anyways, you can see that these are in wildly different places in the file. The first one is about 3.2 million bytes in, and the second one is about 355 million bytes in. So they're in like completely, so these like last 2 bytes of this chunk got stored way, way, way far away in a huge file. Interesting. Um, Not wildly uncommon. Well, actually, this linked block example is extremely uncommon, but it does exist. So anyways, and this also shows something about the nature of chunked data in general. We have a tendency to imagine that they're always contiguous, and this is not the case. There can be large spaces between the different chunks that make up the data for a particular variable. And we're getting close to the end. I know this might be kind of rough going, but anyways, here's some string array data, and here we can see how chunked string array data, how we get some extra information, because for fixed length strings, we need to know the length of the string, and we need to know how, if the string isn't, in this case, 8 bytes long, if it's only 5, what's it padded with? And so we can have null pads, we can have 0 pads, and we can have a space pad. Um, Also, there are varying length string arrays. And in that case, we actually encode the values using ASCII and XML elements. And so we use the element V to wrap a particular value, and we use the optional attribute C to indicate run length encoding. So in this example, the array contains 10 elements. The 0th element is banana. The first element, the 1 element is bread. 2 is the word is. Then the 4th, 5th, 6th, so on element is so, and then the 10th element is tasty. So that's the way we encode run length limited encoding. And this is a particular optimization that we found was very useful for NASA's data, because they have a tendency to have very large arrays of varying length strings that indicate flags associated with different operations. So there might be an array that's 1,000 by 1,000 of these flags, and 99% of them might be a single repeating value, and there might be 3 or 4, 1% or whatever you want to say, that are slightly different. So this kind of run length limited encoding is is pretty easy. And of course, even if it's well, yeah. So, all right then. So those are the basics of DMR++ from a technical point of view, and pretty detailed at that. And then there's some of the outlier stuff. And I think I covered most of the outlier material. Um, what about developing a standard? Like, how does knowing something like this help us develop a standard? And so the first thing is when you hear something like this, we could begin to tease apart things and say, okay, what does a chunk manifest really have to have? What features of DMR++ must be present in any chunk manifest for it to work? And what features does it have that are really optimizations? Like we did these things because of NASA's data store. I mean, do we really need to support some of the things in HDF4? It might be that HDF4 isn't the only data format to have like the block or the linked block notion in it. There might be others out there. We know pretty much that when we get to talking about Kerchunk, we're going to hear about how it handles things like NetCDF and GeoTIFF, and I'm going to guess that they don't have anywhere near the complexity of HDF4. So it might well be that blocks, linked blocks, that notion not really needed in a standard or in a content standard for chunk manifests. Um, we might say, varying length strings, maybe not that important. Maybe they are important to people. We have to decide on that. That's part of our group's mission. So suppose we decide that some things are out of scope. I think we will. But how does an implementation of the standard handle things when it comes up against an organizational pattern that's out of the scope? Because we would like for things that adhere to our standard to have a relatively high level of interoperability. So we would like for some reasonable sort of fallback position to be supported. Um, so one thing you could do is you could just say, well, that variable is very strange and it's in the file, but you can't access it in this way. You can't access it with a chunk manifest. Is that, I think we need to know if it's okay that maybe 0.1% of the variables in a very large granule are not accessible. Um, when we were working with NASA, there was a baseline expectation that we would support everything as it was when the servers ran on premises. So we may have because we extended the implementation to cover cases that were outliers, that may not be appropriate for a standard. So then another approach to just simply marking something as inaccessible or possibly a companion approach would be that an implementation would devise and then propose an extension. We would say, this adheres to this chunk manifest standard, and it also implements this particular extension. And so when you get the chunk manifest from this source, you may see this extension in there. And if you don't understand that, well, okay, then you have the fallback saying that's not accessible. Maybe that's a way to go. The problem is that optional features have a tendency to make standards less interoperable, even though the idea is it's supposed to broaden the scope of things that you describe. Oftentimes it doesn't work out that way, especially when they introduce new data models. So if the data model stays the same, but it's got some obscure quirk, that's fine. But if you bring in like some of the OGC standards had an optional thing where they worked with two-dimensional data, but then they could optionally work with n-dimensional data. Well, software that is really only rooted in a two-dimensional world doesn't really understand n-dimensional data very well. And so there was an interoperability problem with that. I got a minute left. my 40 minutes. You guys are like completely silent and very patient. Um, Thanks. And do you have any questions? And I think I'm going to stop sharing at this point.
Yeah, thank you so much, James. That was great timing. Yeah, thank you for that. And if you have questions, this is the time. Comments. I see that there's some comments in the chat. I can read them out loud if you prefer so, or if Christine wants to start this conversation, you're also welcome to do that. I see people raising their hand.
Oh, yeah, okay. So, I'm still sharing, which means I have the sort of the bottomized view. Okay, here we are. Hands raised. Okay, I'm gonna say, Christine, did you raise your hand first?
I don't know if I raised it first, but I had the first comment. So,
Okay.
Yeah.
um, so this was great. Thank you. I'm surprised you aren't base 64 encoding the fill value. Have you run into issues with that? Because like I have in the past, not in the DMR PP, but in other things when I haven't.
No, we're not. We're not base 64 encoding the fill value. We just put it in
Right.
as ASCII. Huh. That could be an issue, huh?
Yeah, we ran into it. There was a product, may have been an Airs product. I don't remember, but it had like a funky fill value that was not like easily encoded in base 10. And
Yeah.
so that was more of a comment. And I guess the other question is HDF. It sounds like HDF doesn't allow Unicode. That's just like my ignorance.
It could be. I'm not sure. But I do know there's one thing that I kind of glossed over, and that's that there are some things. If you look in the XML schema, which is that's a lot of fun. But anyways, if you look at an XML schema for DMR++ for that namespace, one thing you'll notice is that we treat structures in a special way. And so DMR++ supports arrays of structures. And that's great. But it turns out that arrays of structures have an unusual fill value. And so we represent that fill value as a space-separated set of values. And it's got an interesting semantics. It's complicated to explain, but it does have interesting semantics. It might be something that would be better done as base 64 encoding. It's kind of hard to say, though. So, anyways.
Yeah, for us, like I said, it was mainly just the problem of going, taking something that doesn't have that doesn't make a nice base 10 string for fill value, so that when we
Right.
converted it back to, a float 32 or whatever, it didn't actually match exactly the values in the binary values in the file, and so we ran into
Right.
problems with that.
Right, exactly. So that's a problem with floating point representation for certain numbers. Yeah, right. You
Right.
convert them to a string and it doesn't work out right, so then you get off. Yeah, okay. Good point. Ed.
Yeah, thanks. I kind of have a follow-up question on field values, maybe a little bit more simple. And again, yeah, thanks for this nice presentation, Jim. I learned a lot about DMR++. But my question going back to the field values, should those be the same as the actual field values encoded in the data variable, or does it make a difference? And also, I'm assuming things like not a number are forbidden. Is that true?
Um, Actually, I think Kent would be the one to answer that question,
Kent?
but about the not a number. But when you say the actual fill values encoded in the variable, you mean the underscore fill
Yeah,
value attribute.
yes.
So the fill values that we're talking about here are the fill values that are embedded in the HDF5 metadata. So
Okay,
that's the syntactic metadata of the variable. So
okay. Different.
in say netcdf3 or in CF, fill value is more of a semantic thing, right? You can put the value in there and that's good. But in HDF5, if a particular chunk has only fill values, it won't be written to the disk. There won't be any, it's not like HDF5 fills up 100 or 1,000 bytes with 999 and writes it to the disk. It just says the fill value is 999 and this thing doesn't exist. There's nothing else in there. And so it's a little bit different. It's a little bit different than the NetCDF notion of fill value. You would think, you would assume, you would hope, I'm not sure which of those words is correct, that they would be the same value. You would want that to be the case, I think. But they are operationally different.
I see. Yeah. Thanks for that clarification. And how about the not a number thing? Is that legit?
I don't know.
For HDF5 chunks, or not?
I would think that it would be legitimate for HDF5 chunks, and I would think we would just use the string value, which is NaN.
Yeah. But you might run down the road like different software kind of interpreting what that number not a number actually means.
They could be.
I think it is the potential issue. It's not recommended anymore to put NaNs as a fill value, the attribute, and use it actually in the variable itself.
Right.
Although I think there's still some edge cases where people still do that.
Sure.
Okay, I made my point. Say great. Thanks a lot, guys.
All right. Thanks, man. Christine, did you have a question?
Well, just a comment on fill value. Like in the IEEE 754 standard, which is what basically everyone uses for floating point representation, NaN is a very specific bit pattern.
Yeah.
So there is no actual confusion in the encoding. But when you are dealing with this NaN standard, IEEE, I believe, again, specifies certain ways in which it is interpreted that can make it harder to write code in some ways. And so some people, particularly the person I know is Charlie Zender for NCO, absolutely hates the idea of NaN as the fill value.
Right.
But I have created netcdf files that are, netcdf4, so therefore HDF5, that use a fill value of not a number. I think Xarray does this by default, or it did. And, it created a valid HDF5 file. So, I mean, personally, as somebody with an electrical engineering background, it seems logical to use NaN to me, but I realize I have somewhat lost that argument at this point.
Yep.
Yeah, I think that's a big but there. Yeah, thanks for that clarification too, Christine.
Okay, well, I'm not sure what you guys think about some of the other questions I asked. Like, how do we deal with places where these things differ? Well, I'm pretty sure we know that Kerchunk does not list the filters in the order they're applied. So I'm not sure it will deal with the deflate case, or like shuffle deflate, or